Okay, so now that I've gotten rid of the YouTube videos and I'm not going to get copyrighted, we can go to chemistry. Who's already done the assignment? Nobody? Some people have been getting on early and getting it done. It's not going to take you very long. It's not going to take you very long. I just want to go through this. Like I said, this is going to be relatively easier than what we've been doing, but don't slack off on it. This is the one you really want to pay attention to because you get this stuff. It's going to be easy. You're going to get good grades. You're going to pad your score up and make sure that everybody gets the grade that they want. So what we're looking at today is kinetic molecular theory. And this is our overarching idea, and I want everybody to kind of drive this in because this is what all of what we're going to talk about is about. What does kinetic mean? Yes, kinetic means motion. When we're talking about kinetic versus potential energy is stored energy. Kinetic energy is energy in motion. So literally this is reading kinetic molecular theory. This is the theory of the motion of molecules. That's what we're looking at. That's our overarching thing. So if I ask you a question or Sapling asks you a question, I want you to think about how your molecules are moving. That's what we're kind of discussing here, the movement of molecules. So we start off with our definition, a theory based on the concept that particles are in constant motion. Specifically, we're going to talk a lot about gases. There might be some discussion of solids and liquids, but mostly we're talking about gases. And let's be honest, is this brick interesting? No, it's been here forever. It'll be here forever. It doesn't do anything. It just sits there. It's boring. It's boring. But gas, we can't see, but it's doing interesting things. If I spray this cleaner over here on the board, given just a couple minutes, will y'all be able to smell it? Yes, but why? Like, why? I sprayed it over here. It's not supposed to go over there. What's the point in even having a sprayer if I spray things and they're just going to go everywhere? Why does that smell get everywhere? Why, if someone sprays perfume in a classroom, does it go everywhere? It goes into everybody's nose. You can't hide from it. It's going to get in there. This is why. Kinetic molecular theory. Gas particles are in constant motion. They're never, ever going to stop. If they're in constant motion, they have kinetic energy. That's what we're looking at. This is important. They're going to move quickly and randomly in straight lines until they hit something. So just like if I throw a bouncy ball, it's just going to go wherever I throw it until it hits something, and it's going to bounce off and go somewhere else. So when I let go of a gas particle, it's literally just going to go in whatever direction it's going to until it hits something, and it's going to bounce off that thing and go in a different direction. So it hits something else, and it's just randomly going to bounce around the room until it either goes in your nose or it hits something and gets absorbed. That's what gas particles do. So when we watch this little video, the yellow particle is just going to go in a straight line until it hits something else, either the walls of the container or another atom. It's never going to slow down. It's never going to stop. It's always going to be bouncing. This is what gas particles do. They will change direction but continue in a straight line after a collision. And these collisions are elastic. What that means, if I throw a ball, if I do throw the bouncy ball around here, is it going to bounce forever? No, it's eventually going to stop because every time it bounces, it loses some energy. The same way, if I drop a tennis ball from this height, will it ever touch my hand when it bounces back? No. Every single bounce is going to be just a little bit lower than the bounce before until it eventually falls down to the ground and stops. Gas particles don't do that. This yellow particle will bounce around in this container forever and never stop and never slow down unless I take the lid off or unless I change the temperature. It's going to do what it's doing essentially nonstop forever unless I change something. It's never going to stop. It's never going to settle at the bottom. It's a gas. It's just going to keep going forever. Is everybody okay with that? So just remember that. Gas particles do things differently than bigger molecules that we're used to. So they're going to move forever. They're going to go in straight lines until they hit something, and then they're going to bounce off and go in another straight line until they hit something else. Kinetic energy is determined by mass and velocity. This is a physics equation. We will not use this equation, but one of the good news is we will have some nice, easy equations to use for these sections. You just got to get used to using them, and it'll be a lot easier than stoichiometry. The main thing I want to drive home here, your kinetic energy is about motion. It's obviously the faster you go, the more kinetic energy you have. It's also about mass. The bigger I am, the more kinetic energy I have. If a fly hits me, does it hurt? No. The fly could be going pretty fast, but it's not going to hurt because it has no mass or very little mass. And so there's very little kinetic energy. If a car hits me, even going slow, like a good 5-10 miles an hour, it's going to hurt because the car has a huge mass. And so even at a slow velocity, it has a lot of kinetic energy. It's going to knock me down. That's the difference. Remember that mass plays a part. The bigger something is, the more kinetic energy it can have, even if it goes slower. So lighter things will go faster, bigger things will go slower, but kinetic energy kind of takes in everything into account. Now, what's the big deal? What are we getting at here? Temperature is what we're getting at here. Temperature is the measurement of average kinetic energy or how much you're moving. And this is a good example. Or I think it's a good example. Maybe it's a terrible example. I don't know. These bricks are boring, but they do interesting things. Atoms inside them do interesting things. Specifically in a solid, when, as far as I'm concerned, nothing's moving in here. Like if I take a chunk out of this brick, that space that's missing isn't ever going to go over here or move around. The atoms are stuck together. They're not ever going to move. What makes this brick hot or cold? Like let's say I warm this brick up and it's like 100 degrees and this brick over here is like 30 degrees. What's the difference between those bricks? What makes this one cold and that one hot if none of the atoms are moving and everything's stuck together? Well, what that is, there is motion. It's just on a different level. So in a solid, all of these atoms in every brick, all of the atoms ever, anywhere, period, are always moving, even if they're trapped in a solid. What's happening in these bricks? The atoms are stuck together. They can't move. That's a solid. They can't move relative to one another, but they're vibrating. And that vibration is literally what your temperature is. It's your kinetic energy. When you measure kinetic energy, that's your temperature. So the faster something's moving, the higher the temperature is going to be. The slower something's moving, the colder the temperature is going to be. And in a solid, that movement isn't like moving back and forth like air. It's just vibrations. And so a hot thing, when I touch it, the reason it feels hot to me is because the atoms are vibrating really fast. And when I touch it, those atoms are hitting my hand. I'm not feeling it like pressure, but I'm feeling it transfer that energy as heat. And so the faster moving molecules, I will feel more heat. The slower moving molecules will feel cold, and they might even take heat out of my hand and kind of warm themselves up and get moving a little bit faster. But remember, temperature is literally measuring how much your atoms are moving, how fast they're moving or how much they're moving. That's what we're telling you when we tell you a temperature. We're going to deal a lot with temperature in a little while. Let's see. Okay, this is important. All gas particles have the same average kinetic energy when at the same temperature. So when looking at the periodic table, if I say I have every single element at the same temperature, let's call it 100 degrees, every single element will have the exact same kinetic energy. Now remember, kinetic energy is not speed. They will be going different speeds, but they will have the same kinetic energy. And what that means is the lighter atoms will move faster. So my stuff at the top, like hydrogen and helium, they have less mass, but the same kinetic energy. That means their velocity is faster. They're moving quickly. Your lower elements down at the bottom, the bigger they are, the slower they're going to move. They still have the same amount of kinetic energy, but the bigger stuff moves slower. The smaller stuff moves faster if the temperature is the same. Now, they just kind of talked that average Yes. So they just like hammer this home. The temperature is how much your molecules are moving. If they're moving a lot, they have a high temperature. If they're not moving very much, they have a low temperature. The last thing they want to put together is what are the particles doing? Remember from our solid, liquid, gas phases, gases have particles that are moving around, and there's lots of space in between them, and they don't clump together. They're just always moving around in here, bouncing off of everything, always moving. They don't clump together, and there's lots of empty space in between them, which is why we don't really see gases very well, because there's not a lot to see. There's a whole bunch of empty space. So keep that in mind. Also keep in mind that the reason they diffuse or spread out, like I was talking to you, spray perfume over here, eventually everyone in the class is going to smell it because of that random motion, because they never stop moving. They're always heading in some direction until they hit something else. It's only a matter of time before this perfume bounces off the walls, bounces off of stuff, and finds itself going up your nose. And then your receptacles get it, and your brain processes it and tells you it smells good or bad, whatever you think. That's the diffuse thing. So they're always going to spread out. If I put gas in a container, it's not going to sit at the bottom like water. It's going to go up and go everywhere. Now, that's the end. Don't start on the assignment yet. Give me just one more video. You'll like this, I promise. Or maybe you won't. I don't know your business. If I take, like I said, if we have the same elements, not the same elements, if we have the same temperature, but lighter elements, they're going to move faster, right? And you see this, if I were to breathe in an element like helium, which is literally the second lightest element there is, if I breathe in an element like helium and I speak, what happens to my voice? It gets higher. Like, have y'all done this? If you haven't breathed in helium and spoken, you got to do it as an adult. You will just laugh for minutes and minutes and minutes. It's crazy. It sounds so weird to hear your voice sounding different. But the reason that happens is because helium is light. And just like I can hit a baseball with a baseball bat, but if I hit a golf ball with a baseball bat, it's going to go faster and farther because there's less mass for me to move. When I'm speaking, my vocal cords are vibrating. They're hitting the nitrogen and oxygen in the air, and it makes a tone for my voice. But if I breathe in hydrogen, when my vocal cords vibrate, they hit those hydrogen atoms, and the hydrogen moves faster. It goes out of my mouth faster and into your ear faster, and you hear it as a higher pitched sound. What if instead of helium, I used an atom that was heavier than oxygen and nitrogen? What would that do? Your voice would go lower. Yeah. Your voice would go lower, exactly, which is what these guys are going to do.
I got a very special video for you today. I'm beatboxing with sulfur hexafluoride, which is
a gas that is 5 times more dense than air.
So 5 times more dense than air.
Slower sound travels through it.
It's hopefully going to make my voice incredibly deep, like a demon.
Any type of
like
gas that you put in your lungs that replaces oxygen, you don't want to do for too long.
So that's why I have a resident expert here to make sure that...
First off, does that guy look like a resident expert of anything? No. Maybe he is. I'm being mean, but this is kind of dangerous. Don't do this at home. Obviously, you can't buy this at the store. But because it's so heavy, if you breathe it in, it's literally going to sit at the bottom of your lungs and not move. So you have to make sure you get it out of your lungs or it's going to be bad for you. But listen to what happens when you breathe it in.
Beatbox with sulfur hexafluoride.
First ever.
The world's first.
Take your own in. Hey, but before you do it, doesn't it feel weird? Like hold the balloon. It doesn't go up, it goes down.
It's heavy, like you can feel it. It's weird.
Oh my God! Oh my God! This is not weird.